Hello everyone, Dr. Hasbullah here, and in this video we are going to be looking at a few examples on how to find the major loss inside a pipe. Now let's say that we have a pipe that is 450 meter long. Okay, so this is quite a long pipe and the length is 450 meter. The diameter of the pipe is 38 millimeter. And the pipe is made from wrought iron. Okay, when you are trying to find the major loss, you know that you are going to require the friction factor. And friction factor is depending on Reynolds number and also the relative roughness. That is why when you need to know the relative roughness, you need to know what is the material they use to build the pipe. And also now the flow rate inside this pipe is 2.75 liter per second. And the question is looking for the major loss, that is the head loss, and also the pressure drop. Okay, so head loss is HL, and we know that in order to get pressure from H is simply using the formula P equal to rho times G times H, but that comes later, right? So now, how are we going to find the head loss? Okay, now let me write the equation first. So HL is equal to FL over D V square over 2G. Now, we know that in order to find the friction factor or F, you are going to need to know two things. That is the Reynolds number and also the relative roughness, right? So Reynolds number is velocity times diameter divided by nu. So the first thing that we need to find now is velocity. But we do have the flow rate and we also have the diameter. So Q is equal to velocity times area. So velocity is simply Q divided by area. So Q is, remember that this is in liter per second. So we need to convert that into meter cube. So to convert liter to meter cube, just divide it by 1000. So this will be 2.75 times 10 to the power of minus 3. Divide by, our area is pi times the diameter is 38 millimeter. So this is 0.038 square divided by 4. And we're going to get V equal to, so 0.03 divided by 4 times pi and 2.75 times 10 to the power of 3. So the answer. So that will be 2.42 meter per second. Right, now that we have the velocity, we know that we have the term here. And then I think we know the diameter, that is 38 millimeter. And then what we need to know is the kinematic viscosity. And quite simply, this is something that you can remember, similar with how you remember the density of water, which is 1000 kg per meter cube, density of air, that is 1.2 kg per meter cube, and the viscosity nu of water is equal to 1 times 10 to the power of minus 6. And the unit is Pascal second, right? So I think we have everything that we need in order to find the Reynolds number. So let's find it. Reynolds number is equal to velocity, that is 2.42 times diameter is 38 millimeter. But remember to convert it into meter. This is 0.038 divided by 1 times 10 to the power of minus 6. So you end up with the Reynolds number of 2.42 times 0.038 divided by 1 times 10 to the power of minus 6. And we end up with 92,000. Okay, so 92,000 is quite far from 4,000. That is our critical point between laminar and turbulent. So this flow is definitely turbulent based on the Reynolds number. The next thing that we need to find is the relative roughness. That is E divided by D. And for the relative roughness, we need to know the material, that is the wrought iron. So to find the relative roughness of the wrought iron, let me bring you to our Moody chart. And inside the Moody chart, look for this region. Okay, this is where you can find the relative roughness, or this is where you find your surface roughness, that is E. Now, we know that we are looking for wrought iron. So, our E is 0.046 millimeter. Remember that the unit is in millimeter. Okay, so 0.046. So, 0.046 and unit is in millimeter. And the diameter is 38 millimeter. Now, the unit must cancel out. Okay, so if you set the unit to be in meter, everything has to be converted into meter. But since now we have millimeter as the unit, so let's just use millimeter. So this is 38 millimeter. So our relative roughness is 0.046 divided by 38 millimeter. So that will be 0.0012. 0.0012. And remember that Reynolds number and relative roughness does not have any unit. Now, in order to find the friction factor, we know that we need these two parameters because we want to use this inside the Moody diagram. Okay, now I'm going to copy this and bring this to our Moody diagram. So I'll just paste it here for our reference in case we forget about these values. Okay, now, first of all, we need to find the Reynolds number. Right, and our Reynolds number is 92,000. Now, if you haven't seen a log scale before, okay, the Reynolds number is here at the x-axis. So you need to be careful because this is log scale, meaning that this is 1,000, this is 10,000, this is 100,000, this is 1 million. And our Reynolds number is 92,000. So 92,000 must be between 10,000 to 100,000. So you need to be careful because very often I see that people, instead of looking for 90,000 here, they are looking for 90,000 here. Okay, so that is a mistake. So be very careful. So what I'm going to do now is to find where is 92,000. Right, so let me zoom in. So this is 10,000. This is 20,000, 30, 40, 50, 60, 70, 80, 90. Now, between 90,000 and 100,000 is a very little space. Okay, so it's okay to follow this 90,000 even though our Reynolds number says 92,000. So it's close enough. Okay, so for 90,000, let's just follow this line upward and see where this takes us. Right, but before that, we also need to find our relative roughness. This is 0.012. Now, sorry, this is 0.0012. Now, this is another mistake that I see students make, which is the number of zeros. Now, this is 0.0012. So, 0.0012 should be in between 0.001 and 0.002. Probably somewhere here. That is 0.0012. But I think the line is close enough to 0.001. So we are going to follow the 0.001 line until we see where it meets with our Reynolds number. Okay, so I'm going to color this as purple. Right, so we're going to follow the 0.001 and we need to follow this curvature of this gray line. Okay, and we know that it's going to meet our Reynolds number over there. Let me extend this line for Reynolds number. Okay, and it will meet here. Now, we know that 0.0012, the relative roughness, is a little bit higher than 0.001. So, I'm going to say that my point, my exact point is probably here. Okay, a little bit higher. Right? So, what I do next is to draw a line to the left-hand side of the diagram. Okay, that is where I'm going to find my friction factor. Right, so if I use orange here, so I'm going to follow this line to the left, and this brings me to the F value of 0.023. Okay, now let me get back to our notes. Now we know that the combination of these two parameters will give us the friction factor of 0.023. Now I think when we have the friction factor, we can finally solve this equation. Okay, so let me write that again. HL is equal to FL over D V square over 2G. So now F is 0.023. L is the length of the pipe, okay, and the length of our pipe is 450 meter. 450, and now remember that everything is now in meter, divide by 0.038, that is the diameter of our pipe, times the velocity. I think we've calculated velocity before, 2.42. Don't forget the square, divide by 2 times 9.81. Okay, now let's try to get our major loss. 0.023 times 450 times 2.42 square, divide by 0.038, divide by 2, divide by 9.81. That will be 79.2. And remember that the unit for head loss is meter. Okay, and I believe now that we have solved question A, that is our head loss. So our head loss is equal to 79.2 meter. And how do we find pressure drop from this head loss? It's quite simple because we have done the hard work. So pressure loss is rho times G times HL. That is 9810 times 79.2. That will be times 9810. That is 777.1 kilopascal. Right, so that is the pressure loss. So I believe now that we have solved both question A and question B. So now I hope that you can see the workflow that we have gone through in order to find the head loss and pressure drop. The key now is to find the friction factor, or F. And in order to find the friction factor, we need the Reynolds number and also we need the relative roughness. Once we have that, we use that value and find what is our friction factor using the Moody chart. And once we have the friction factor, we have the head loss, and from head loss, we can easily calculate our pressure loss. Now, this example is quite straightforward where all the parameters are given to you and you can simply use that flow that I described just now in order to find the head loss. But what if the information is the other way around? Now, let's take a look at our second example. Now, for question 2, what you have here is also a pipe, but now the length of the pipe is 300 meter. And the diameter of the pipe is now 100 millimeter. Now, the information that's been given to us is that the pressure drop that occurs across this pipe is 700 kilopascal. And also, this pipe is transporting oil that has the specific gravity of 0.9 and also the nu of 1 times 10 to the power of minus 5 meters square per second. Now, with the information that's been given to you, determine the flow rate inside this pipe. So the question is asking for what is the flow rate? And also the material that is used to make this pipe is also wrought iron. Okay, now how do we solve this problem? Now, first of all, let's look at the equation for flow rate. This is Q equal to velocity times area. I believe we already have area because the diameter is given, that is 100 millimeter. But we do not have velocity. And how do we find velocity? It has to be from our losses. That is HL equal to F times L over D times V square over 2G. So this is where we find our velocity. But now, what we do not have, or what we do have now, is the length, which is 300 meter, the diameter, that is 100 millimeter, and gravity we have. We also have the HL, because we can get that HL from our delta P. Now, the problem is we do not have the friction factor. And in order to find friction factor, we need Reynolds number and also we need the relative roughness. Okay, and Reynolds number is equal to VD over nu and relative roughness is equal to E over D. And E, let me take a look at our Moody chart, still wrought iron, that is 0.046 millimeter. So 0.046 millimeter divided by diameter is 100. That leaves us with 0.00046 as our relative roughness. But to find the Reynolds number, we need velocity, we need diameter, and we need nu. Of course, we have diameter and we have our kinematic viscosity. So without Reynolds number, how do we solve for our friction factor? Okay, now this is the tricky bit. Now, first of all, we're going to make an assumption and then we're going to correct for it. Okay, so we're going to make an assumption that the Reynolds number is very high. Okay, so what happens to our Moody chart when the Reynolds number is very high? So what happens now when the Reynolds number is very high? If you notice, this line is flat. Okay, it doesn't curve a lot when Reynolds number is very high. Right, now let me clear that up for you. And I'm going to delete this as well. Now, where is our relative roughness? Our relative roughness is 0.00046. Okay, now let's go back to our Moody chart. So our relative roughness is 0.00046. Okay, now where is it? I believe that it's here, between 0.00046 and 0.006 over here. Okay, and what we do now, because we assume that our Reynolds number is very high, okay, what we can do in order to get our first friction factor is simply just interpolate the graph to the left hand side, right? So I'm going to follow this line, okay, 0.00046, okay. So I'm going to follow this line to the left. Okay, and I'm going to get my friction factor here, but this is actually between 0.004 and 0.006. So probably is a little bit upward, that is here. Okay, so that's what we're going to do here. So it may be here. Now, our friction factor now is about 0.0165. Okay, so don't worry if you choose 0.016, because the best we can do with a diagram this small is to approximate. Okay, so now I'm going to take f equal to 0.0165. Now remember that this f is not final. It is based on the assumption that our Reynolds number is very high. Okay, we still need to find what is our actual Reynolds number before we find out what is our actual f, right? So 0.0016, let me get back to our notes. Now f is 0.0165. Okay, and when we have f, of course we can find what is our velocity, right? Our velocity is going to be HL times d times 2g divided by f times L square root. Okay, and our HL is actually delta P is equal to rho times G times HL. So HL is delta P over rho G. Delta P is 700 kilopascal. That is 700,000 divided by rho G. But remember now, this is oil with specific gravity of 0.9. So our density now is 900 times 9.81. So what is our HL? This is 700,000 divided with 900 divide 9.81. That will be 79.28 meter. Okay, and I'm going to plug this inside this equation in order to find our velocity. So HL 79.28 times D, diameter is 100 millimeter, this is 0.1, times 2G, this is 9.81, divide by F, our F is 0.0165, divide by L, and our length is 300 meter. So this is 300. And square root everything. And I'll end up with the V of 79.28 times 0.1 times 2 times 9.81 divided by 0.0165 divided by 300. Square root of that. We have here velocity of 5.61 meter per second. Okay, and that is our velocity. This is our assumed velocity. Now, what do we do when we have our first velocity? This is the time where we find our first iteration of Reynolds number, because now we have the velocity. So Reynolds number is equal to velocity of, let's use this equation. So velocity is 5.61 times diameter is 0.1 divided by the kinematic viscosity, that is 1 times 10 to the power minus 5 meter square per second. 1 times 10 to the power minus 5. That gives us the Reynolds number of 0.61 times 0.1 divided by 1 times 10 to the power of minus 5. 56,100. Okay, so this is our Reynolds number and this is our relative roughness. So let's use this combination and find what is our F, or friction factor, for the first iteration. Okay, so 56,100 should be about here. So this is 20,000, 30,000, 40,000, 50,000, and this is 55,000. And remember, our Reynolds number is 56,100, so that's close enough to 55,000. So I'm just going to follow this line. And let's just go upward a little bit more. And our relative roughness is 0.00046. So that is here. Okay, I'm going to use orange line. Let's make it thicker. So 0.00046. I know that my end line is going to be a little bit above this line. So I'm just going to follow this curvature. And it ends up here. Okay, the line is meeting the Reynolds number line here. Okay, so it's about this line. And I'm going to draw a line to the left to find what is my friction factor. What is my new friction factor? And it turns out my new friction factor is about 0.02. This is 21, 22, 23. So 0.00225, or you can do 0.023 as well. It doesn't matter. Now, when I have this friction factor, let me go back to our notes. So my new friction factor is now 0.0225. And of course, with this new friction factor, I can find out what is my new velocity, isn't it? So velocity, I'm going to copy this formula over here. Okay. Now, velocity is equal to HL is, what is our HL? It is 79.28 times the diameter is 0.1 times 2 times 9.81 divided by my new F, that is 0.0225 times L. L is 300. Okay, and square root of all of that, and I'm going to get 9.28 times 0.1 times 2 times 9.81 divided by 0.0225 divided by 300, and square root of that, 4.8 meter per second. Okay, and what do we do after we find the velocity? We can find our new Reynolds number. So our new Reynolds number is now velocity times diameter divided by nu, that is 4.8 times diameter is 0.1 and nu is 1 times 10 to the power minus 5. That will be 48,000 this time. And using this Reynolds number, if I use orange this time, and using the combination of this Reynolds number and this relative roughness, you're going to find a new friction factor. Now we need to check if the friction factor is similar with what we obtained previously. Do you see where this is going? If the friction factor match, then the iteration is completed and we can accept that the velocity is correct. If it doesn't match, we need to use that new friction factor to find the velocity and then find the Reynolds number again and then check again whether the friction factor match our previous iteration. Okay, so now let's do this first. Our Reynolds number is now 48,000. Let's go to our Moody chart. And 48,000 is about here. Let's use purple this time. So 48,000 should be about here. Okay, so let's draw this line and let's follow is close enough to our previous assumption, okay, and it meets here. Okay, it meets at this line. So a little bit above our previous friction factor. And if you notice, there's only very little difference between our previous friction factor and the friction factor that we have now. If I were to see it very closely, and it could be, my new friction factor could be 0.022, maybe 55. So I think it's close enough and that we can accept this to be our final friction factor. We don't have to go any further because it's only going to get closer and closer. So because of that, we're going to accept F equal to 0.0225, and we're going to find velocity from this value, and we're going to find our flow rate. So our new F is also 0.0225, right? And this will give you the velocity of 4.8 meter per second, right? And remember our original intention, that is to find the flow rate, which is Q, and Q is velocity times area. Finally, we can do that. Now, Q is velocity is 4.8 times area, that is pi times 0.1 square over 4, and we end up with Q of 4.8 times pi times 0.1 square divided by 4, that is 0.0377 meter cube per second. Okay, and that is our final answer to this question. Now, I hope you can see now that this question is a little bit different than our previous example. Our previous example is quite straightforward, where everything is given and you only need to find the friction factor in order to find the head loss. But in this problem, the head loss is given to you. So now you're going to have to assume a few things in order to find the actual friction factor and also the actual velocity and the actual flow rate. Now, this is quite tedious. It requires iteration. Now, we did 2 iterations, but sometimes it requires 3 iterations, but very rarely it requires 4 iterations. So 2 or 3 iterations is fine. So as usual, do this example again and again until you understand how to do it even without looking at the equation. That is all from me for now, and I'll talk to you soon. Bye!